Hello everyone. In this section we'll be looking at universal gravitation. So now that we know something about how weight works on Earth and what the Earth gravitational field looks like, let's look at some other objects and gravitational fields in different parts of space and how that affects the weight of different objects. So, Newton realized that all objects with mass, not just the Earth, produce a gravitational field. The gravitational field, like for the Earth, will be pointing inward toward the center. The strength of an object's gravitational field is proportional to its mass, which sounds a little similar to the strength of a force on an object in a gravitational field. So it means that heavier objects will have stronger gravitational fields. Make sense? And conversely, lighter objects, like, apples or people, will have much, much weaker gravitational fields. This means that if we have something smaller than the size of about a planet or a moon, then the gravitational field around it will be so small as to be almost non-existent. So Newton now had all the pieces he needed for the universal law of gravitation. He knew that there was a force due to gravity, that it was proportional to an object's mass, and he knew that that field spread out as you went further away, and he knew that all objects created it. So the gravitational force on an object is proportional to its mass and proportional to the field strength. We don't really have an expression for this field strength just yet, but we have the mass. So we'll say the force on gravity is proportional to the mass of the object, right? We also know that the field strength gets stronger for more massive objects, like planets. So we can say that the force is proportional to the first mass, which is in the gravitational field, and the second mass, which is producing the gravitational field. With me so far? Alright, finally, we can say that the field gets weaker with the square of the distance from it, because we can imagine a sort of sphere around the Earth that gets bigger as we get further away. The surface area of that sphere will increase by 4 times if we double our distance from it, because the surface area is proportional to the square of the radius. So that means that we can put an r squared over here, where r is the distance to the center of the planet. Make sense? Gravitational field gets weaker the further away we are. So that's the r squared. Now, we still just have a proportion here. We have the force is proportional to m1, m2 over r squared. So we need to put some sort of constant out the front. So then we can put an equals sign, because we know that if it's proportional to m1, m2 over r squared, then if we multiply that by a constant, then we should be able to get an equality happening, assuming there aren't any other variables. The other purpose of the constant, called the gravitational constant, is to turn the units into the right sort. So at the moment we have kilograms squared over meters squared. What we need is newtons. Newton was able to find the size of this by measuring the other values of the system, the r, the m1, and the m2. And from there was able to calculate the value of capital G, which turns out to be a very, very small number. If you were to write out this number ordinarily, it would be, 0.000000000, and then finally, you'd get the little 6672. So it's a very small number. And the reason it has to be so small is because the Earth's mass is so great. And it needs to sort of cancel out the Earth's mass so that we get a reasonable number for the gravitational acceleration. To calculate this, all you need to do is figure out what g is and know the mass of the Earth and the radius of the Earth. So the radius of the Earth isn't constant. There are mountains, valleys, plains, every sort of thing, right? And at all those different points will be a slightly different distance from the center of the Earth. Additionally, the density of the Earth is not uniform. So even if the Earth was completely flat and there weren't any, mountains or valleys or that sort of thing, it might be that concentrated deposits of metal or something would mean that the ground under your feet is slightly heavier than the ground under someone else's feet. So once again, the gravitational field would be a little bit different. So this means that the acceleration due to gravity varies depending on where you are on the Earth, but only a tiny bit. The other thing is that the Earth is not a sphere. It bulges out in the middle because it's spinning around so fast. And this means that at the equator, we're further away from the center of the Earth. So the gravitational field, the gravitational acceleration right at the equator is only 9.78 instead of 9.81. You can see that it's still very close. So what about the poles? Well, those are a little bit closer to the center of the Earth, so the gravity will be stronger. At the poles, gravitational acceleration equals 9.83 instead of 9.81. But you can see that there's not a huge amount of difference, once again. At the moment, we're talking about, hundredths of a meter per second. So universal gravitation applies not just to Earth, but to all planets and all moons. That's what Newton realized when he figured out the gravitational field was proportional to the mass of the object creating it. The mass of the body can be different to Earth's mass, and the radius of the body can be different to Earth's mass. And remember, these two things are what affects the strength of the gravitational field. The gravitational constant, the big capital G, and the object's mass do not change. That doesn't mean that the weight doesn't change. Remember that the weight is the product of the mass and the gravitational acceleration. So this fellow, even if he's the same mass on the Earth and the Moon, will weigh more on the Earth than he does on the Moon. Well, that's the end of the theory. So in this section, we've gone through Newton's law of universal gravitation and the different elements to it, and what gravity and weight looks like on different planets. Let's go on to some questions. Question 6. How does the mass and weight of an object change as it moves to different locations on the Earth's surface? So for both mass and weight, we have an option between does not vary and varies slightly. Now it turns out that unless you get into nuclear physics, the mass of objects doesn't change. Mass is conserved, right? So that means that the mass does not vary. It's got to be one of the top two options. Now, we know that the gravitational field over the Earth is not quite constant due to the irregularities in the Earth's surface. So that means that the weight can vary slightly. Out of A and B, that means that the answer has got to be B. So this is the correct answer. Question 7. How does the gravitational force on an object change as it moves away from the Earth? So we have a few options. Let's go through them. It gets stronger because it has further to fall. Now, there is something that gets larger as it gains the potential to fall, but that's called gravitational potential energy. So it's not the force on the object. It stays the same because gravitational acceleration is constant. Well, this would be correct, except we know from Newton's universal law of gravitation that as we move away from the Earth, the gravitational force will actually decrease. So it's not B. D says that it gets weaker because there is no gravity in space. This is completely wrong. There is gravity in space. Gravity is what causes the Moon to orbit the Earth and the Earth to orbit the Sun and the Space Shuttle to orbit the Earth. If there was no gravity in space, then none of these processes could occur. Our last option is C. It gets weaker because the gravitational field is more spread out. And this is the correct answer. This is the reason that in Newton's universal law of gravitation, the denominator is r squared. It's a signal that the gravitational field is spreading out as we move away from the Earth. Question 8. At the equator, gravity acceleration is this. At the poles, gravitational acceleration is that. An object has a mass of 80 kilograms. What is the difference between its weight at the poles and at the equator? In other words, what's the most amount of mass you can lose or gain just by changing your location? So at the South Pole, the object's weight will be F equals mg. We know what g is at the poles, and we know what m is. So the force, the weight, is 80 times 9.832, or 786.56 newtons. So that's the mass of an 80 kilogram object at the poles. How about the equator? Well, it'll be a similar sort of thing. Once again, we use F equals mg, but now the gravitational acceleration is given by this number. So its weight will be 782.56 newtons. Alright, so what's the difference between these two? The difference between the weights is the difference between these, or 4 newtons. This is the equivalent of about 400 grams at a gravitational acceleration of 9.81 meters per second. So I'm afraid that you can't really lose weight just by moving. Question 9. Here's the value for the universal gravitational constant. What is the gravitational acceleration on Venus, a planet with this radius and this mass? Now, what's the formula for gravitational acceleration? We know that the formula for gravitational force is F equals g m1 m2 over r squared. But we also know that to find the gravitational acceleration, that's got to be the lowercase g of this equation, where this is the m1. So to find the gravitational acceleration, what we need to do is find the value of this other expression. Make sense? So gravitational acceleration equals g m2 over r squared. And we can just derive that from the law of universal gravitation. So we can substitute in these values, capital G, m2, and r. And now our equation looks something like this. We can use a calculator to evaluate that. It'll turn out to be 8.87 meters per second squared, which is fairly close to the gravity of Earth. It turns out that Venus has a similar radius and a similar mass to that of Earth. Alright, let's get a bit further out now. What is the gravitational acceleration on Ceres? This is a dwarf planet, used to be classified as an asteroid, with a radius of 475 kilometers and a mass of this. So Ceres is in fact the largest object in the asteroid belt between Mars and Jupiter, and is responsible for about a third of the entire mass of the asteroid belt. So once again, we can use this equation to find the gravitational acceleration. And now instead of substituting in these values, we substitute in these values. So our mass will be 9.43 times 10 to the 20, and our radius will be, because we're converting it into meters, 475,000 meters. Right, so there we go. 475,000 meters is the same as 4.75 times 10 to the 5. And this evaluates to 0.28 meters per second squared. A lot smaller than Earth's gravity. Question 10. The Sun has a mass of 2 times 10 to the 30 kilograms, and the Earth has a mass of about 6 times 10 to the 24 kilograms. The distance between them is 1 astronomical unit, or 150 billion meters. What is the gravitational force exerted by the Sun on the Earth? So in this case, we can once again use the law of universal gravitation. In this case, we're looking for gravitational force, so we can leave our equation looking like this. Right, now when we're converting kilometers to meters, all we need to do is multiply that by 10 to the 3. So now our equation looks something like this. And that'll evaluate to 3.52 times 10 to the 22 newtons, which is a very strong force. But remember that we're moving the entire mass of the Earth. So it's got to be a strong force to produce an acceleration that will make it orbit around the Sun. Alright, so that's the end of the questions. In this section, we've gone through how to calculate gravity on other planets and how to calculate gravitational force between massive objects. In the next section, we'll be looking a little more at the sensation of weightlessness and what causes it.